So just a wee bit of review. Yesterday, we were talking about the components of an atom. We know that our protons have the positive charge, neutrons are neutral, electrons kind of found in a cloud and they have a negative charge. We also know that the electrons, weight-wise, really don't contribute anything to the atom. Now, they do contribute a charge. They do make the atom negative because that's what the atom's going to gain or lose. We're not really going to manipulate the protons and neutrons too much. It's really the electrons, either losing an electron where we would become more positive because we're getting rid of negative feelings. And if we take on negative feelings, if we gain an electron, then we have negative charge. And these electrons are found in a cloud in the electron shell. The basic premise behind our atoms is that they want these shells to be balanced. They want to have a full outer shell. And so we know that the innermost shell has how many? 2. And then the shells consecutively after that are going to have 8, 8, 8. And that's really as far as we're going to go. Now, there are 2 elements that we said were inert. And what inert means is that their shells are satisfied. They have no desire to gain, they have no desire to lose. But what that also means is that these 2 elements, it's very difficult for them to bond with other elements, because the way that we bond is either contributing and getting an electron, changing the charges and being opposites attract, or holding hands, sharing is caring, and caring is covalent. There is a very in-depth discussion on Santa right now, and I think that is really funny. Hang on, she's barking and she's going to continue to bark. So let me just grab her real quick. Hey, you are driving me crazy. I'm gonna just let you go like a wild dog and let coyotes eat you. I would never do that. So here's our shells. Oof. And we can see here the 2 that are inert. We've got our helium because we do have 2 in the shell, so it's satisfied. And here's neon 2468, and the shell is satisfied. So molecules, these are when we have atoms bonded together in a chemical bond. And these chemical bonds, like I said, can either be ionic, where we gain or lose an electron, or they can be covalent, where we're sharing electrons. And then we have hydrogen atoms, which is kind of a combination, where we have a covalent bond and we have a difference in charges. So we kind of have a little bit of both. And these different bonds have different strengths. And so some of the bonds are really super weak, very easy to break. Other bonds are much stronger. And the idea is, if you break a bond, you release this little buzz of energy. And so when you start talking about like hydrogen bombs, what is happening is you have a massive amount of bonds that all break at the same time. It releases a catastrophic amount of energy that just takes out everything. So that's just how significant these atomic bonds, the energy, if it is controlled and if it is kind of regulated, just how much energy we can get from these different bonds. Now, when I have 2 or more atoms from the same element bonded together, that is called molecule of the element. So a molecule just simply is atoms bonded together. And now we're doing definitions letting us know what atoms. Are they the same element? Are they different elements? And so a molecule of the element is just going to be 2 atoms of the same element bonded together to make a molecule. Bonds are how these atoms attach to one another. And then if we have a compound, these are made up of 2 or more elements. And I think yesterday we compared a little bit to, they have pharmacies called compounding pharmacies, which is a similar premise where we would have 2 different medications that are bonded together, and that would make a compound. All right, so let's talk about some mixtures, solvents, and solutes. This is how we can kind of combine things together. Raymarie, your dog is ridiculously cute and looks just like my soulmate Bentley, who I lost about 2 years ago. I am in love. Sorry, I got distracted by the dog. This is a technician hazard. You get very easily distracted by animals. All right, so what a mixture is when we mix stuff together. I mean, it's not rocket science. When we mix things together, it's called a mixture. And we have 3 different types of mixtures. And these different types of mixtures are dependent on the size of the molecules that are making them. We have solutions and colloids and suspensions. Oh my, I'm going to go into each one of these in detail. But the big difference between these 3 is the size of the molecules. In these mixtures, if the molecules are very, very small, then they're not going to impede light coming through. You're not going to see cloudy, and they're not going to settle out. Think like a mineral water, right? You go to your fridge, you grab the mineral water. The mineral molecules are so small that when you hold the water up to the light, you can still see through it. It's not cloudy, and they don't settle out. They're still in there, they just don't settle. Colloids and suspensions, the molecules are going to get much bigger. And so that is going to potentially impede light, where it will start to look cloudy. You can't really see through it, and they're going to settle out. So if you leave it sitting, those molecules are going to settle to the bottom. The solvent and the solute. So if we're mixing 2 things together, we have to have a name designating these 2 things. The solvent is the thing that we have in the greatest amount. Water is what we call the universal solvent, meaning that you can mix literally anything in water. The solute is what we're adding to it. So let's do an example. I have a glass of water. That is my solvent. The solvent is the water. I have a teaspoon of salt. I put the teaspoon of salt into the water and I mix it up. The salt is the solute. The water is the solvent. Yeah, Alondra, that's a great example. Oxygen would be a great example of a molecule of the element, because oxygen that we breathe is what? O2. So we have 2 oxygen molecules bonded together. If we have if we have just a compound, which would be 2 different, that would be something like CO2, where you have carbon and 2 oxygen.
I have a question. So if it's like sodium chloride, would that be like a compound or no?
No, sodium chloride would absolutely be a compound, because we have 2 elements that are different bonded together.
Okay.
So here we have, oh, go ahead, Lizette.
So you know how you said that you can add water into anything? Isn't there from what I remember from organic, that is it either you can't add water to acid or acid to water? I forgot.
Oh, honestly, I don't remember. Water being,
you don't add water to acid, you add acid to water, because if you add water, not water to acid.
Okay, I got part of that. So honestly, when I say that water is the universal solvent, I mean, obviously there are exceptions to every rule. So for the most part, most things can be mixed into water or water can be mixed in. Oh, there we go, Charles. Acid to water, not water to acid.
Okay.
Good to
Yeah.
know. That's yeah, when you have water to acid, it could splash out. And then you would become a supervillain. So you definitely don't want that to happen. Well, maybe you do. I don't know.
So in a mixture, you would just define the solvent as just what there's more of?
Yes.
Okay.
Absolutely. Found in the greater amount. And then the solute is found in the smaller amount. And in general, the solute is what you are mixing into the solvent. So here we have our solution. This is the example I gave, is mineral water. And so, excuse me, this mineral water does have particles in it, but they're so tiny they don't scatter the light. And so the mineral water is going to be clear. It won't be cloudy because the particles are too small and they're not going to settle. I could leave this mineral water sitting on my table all day long, and it's not like I'm going to have this big cloudy bunch of minerals in the bottom of my mineral water. So that's the definition of a solution. The particles are very tiny, they do not scatter light, and they're not going to settle out. A colloid. A colloid has a larger molecule. It does reflect light, so you can't see through it, but these particles do not settle. That's kind of what sets it apart from our solution. We do have the larger particles, so it's impeding the light. We can't see through it, but like the solution, they don't settle out. The other thing about these colloids, it's a fun word to say, is they can go from solid to liquid and liquid to solid. And I have this example here of some Jell-O. Jell-O is a wonderful example of a colloid because you get the water, you put the Jell-O powder in the water, you mix it up, you then apply cold. Temperature can affect all of these reactions, cold and heat. So we apply some cold, and that liquid then turns into kind of a semi-solid. And if you then take it to the park for a picnic and you leave it in the sun for a few minutes, it's gonna melt and turn back into a liquid. So the big deal here with the colloids, different from our solutions, big particles, but still don't settle out. And then finally, we have what's called a suspension. And I think about these because they are
I have a
giant.
question.
Oh, yes, go ahead.
What would ice be?
Ice is just H2O. So that would be a compound that is in a solid state.
Okay,
So that is not a mixture. That is a compound.
gotcha.
So the suspension, the molecules are super big. And one of the examples I like to use is blood. Blood is a liquid tissue. Oh, yes, absolutely, Leanna. I can go to the private slide. Is this the slide you need, Leanna? Where did Leanna go? Oh, this one? Which one? Okay. So blood. Blood is a liquid tissue. Blood is really fascinating. I love looking at blood. Not in a creepy way, but in a clinical way. Blood is basically, if you want to go just to the most basic definition of blood, blood is fluid and cells. That's it. You have fluid. Now the fluid is very complex. You have proteins and clotting factors. Oh my, all this stuff. And cells, you have white blood cells, which are leukocytes, and red blood cells, which are erythrocytes, and platelets, which are thrombocytes. They all do different jobs. But for what we need right now, you have your liquid, and your solids.
I have a
I
random
mean-
question about like blood drawing in animals. Like, are there like, because you know, there's like human blood donation sites and plasma sites. Do they do the same thing for dogs, or where do they get their like blood banks?
So that's a great question. It depends on the clinic that you work at. If you work at a specialty clinic or an emergency clinic, you will have a storage of whole blood and fresh frozen plasma. If you work for a general practice, like I worked for a general practice, did we do blood transfusions? Rarely, but yes. In that case, most veterinarians and most technicians, like both my dogs right now are teeny tiny itty bitty. But back then when I was in clinic, everyone had larger dogs. I had a lab, my veterinarian had a lab, and they go in a rotation. You can volunteer, you don't have to. But if we have an animal that comes in that needs a blood transfusion, he would run home and grab his dog's name was Henry. He'd bring Henry in and we would take blood from Henry and then give it to the new dog. The crazy thing about blood donation in our dogs is, and I'm not going to go into too much detail because we're getting a little bit around the cul-de-sac here, but it is fascinating. We don't necessarily have to match the blood type, not for the first time. You get one freebie where I can take the blood from the dog while it is still warm and start infusing it into the dog that needs the transfusion. Now, after the first one, now I got to match it to their blood type because both dogs and cats have different blood types, and we're going to teach you how to do that. But for the first one in dogs, not cats, but in dogs, you get a freebie. And so we would just run and grab Henry, or I would come home and grab Julie, and we would just do a blood donation. You can take up to 750 milliliters depending on the size of the animal. So yeah, it's pretty cool. Pretty cool. So with the suspension, our cells are going to be the molecules. The cells are going to be the particles. You can't see through blood. You can look and light does not pass through. But the big difference with our suspension is if I leave the blood sitting on the counter, the cells are so heavy they will, by gravity, start to settle to the bottom. And in fact, that's something that we want them to do so that we can separate the cells from the fluid. And so the cells will
Question.
separate out. Yes.
So is that what a centrifuge basically typically does, is just kind of speed up the process?
Yep, sure does. It uses centrifugal force to force the cells and separate them from the fluid. So it just speeds up the process.
What do you mean by scatter the light or reflected?
So when I say scatter the light, it means that if I'm holding it up, light cannot penetrate it. The light will come and hit the molecules and not be able to penetrate through, and that's why it's not clear. If we look back here at our mineral water, these do not scatter the light, meaning that the light can easily go all the way through, and that's what allows you to see it's clear. Here they do not allow the light, so the light comes in and goes pew and bounces back, and that's why you can't see through it. Yeah, so the layers are different densities, and that's what allows them to separate. And in fact, our cells have different densities. So here we have a blood that has been separated, and here we have our red blood cells, which are the heaviest of our cells. Right here we have this white line. This is called the buffy coat. And these are the white blood cells and the platelets. They're not as dense, so they don't settle as low. And then here we have our plasma. So this is just a great example, cells of different densities that will settle out. And now we also have a variation of how we're scattering the light, because the molecules are no longer up here in this plasma or serum, depending on what kind of tube you used. The molecules are no longer here, so guess what you can do with the serum? See through it. I can take that serum and put it up to a piece of paper and be able to read the words behind it. But down here, the molecules have all settled. And so this would be opaque. I cannot see through it. I don't know if that's how the Buffy coat could be. Never really got into that show. So a mixture are things that are, this is not rocket science, things that are physically mixed. There's been a lot in the news this past year of having a cough. And you go to the doctor and he gives you the cough syrup. We've all had it. We've all had the cough syrup. And what do you have to do to the cough syrup before you take it? You have to shake it up. You have to physically mix it. That's a mixture. Mixtures have to be physically mixed. So this is two different substances that will settle out, and then when I mix them back together, that is a mixture. So if I took this blood, this suspension that has separated out, and I take the tube and I very gently rock it back and forth, what have I just created? A mixture. I've mixed it together. Anything I have to mix together, it doesn't matter if it's a suspension or a colloid. If I have to mix it together, it's a mixture. Ouch, my jaw just popped. And then, as I said before, I've already gone over this definition. A compound are two different things bonded together. And so again, we talked about the compounding pharmacy, which is where you have two different medications bloop, bonded together in a single dose. If you look at again, some of the cold medications, if you look at like the Robitussin, or I don't even know what the other ones are. I like Robitussin, but it has a bunch of different active ingredients, doesn't it? It has guaifenesin that helps to break up mucus. It might have acetaminophen to take down your fever. It would have some sort of cough suppressant, maybe even a pseudoephedrine. These are all things that are chemically bonded together into one dose. Bam,
Miss Huff,
compound.
Miss Huff, with Tylenol 3, something like with like codeine or whatever, would that be a compound? Like the pure form of it, the solid? Okay.
Yeah, because you would then have acetaminophen, which is Tylenol, codeine. We make a Tylenol codeine jelly sandwich compound. Yeah, we call it, what is it? You called it Tylenol 3. We call them 222s.
Yeah.
In Canada,
okay.
we call them 222s. And here's a fun fact for all of you.
I've never heard of that before.
Yeah, I don't know why we call them 222s. But they're over the counter in Canada.
Are you serious?
Yeah.
That is crazy.
Yeah, you can go now. It's like here where when you go to the pharmacy and you buy like pseudoephedrine, you have to give them your driver's license and you have to sign for it. But yeah, codeine with Tylenol is over the counter. Yeah. You can just go to any Walgreens and buy it. Other medications that are pharmacy here, like there's a muscle relaxer called methocarbamol. That is like super duper regulated. Man, you can go and buy it. It's right next to the aspirin.
Is it because of the way you guys' pharmacy or pharmaceutical process is set up in over here that what we have?
I don't know. I think it's because I don't know. I'm not going into that. Not touching that one. Not getting into a political discussion about healthcare.
Okay.
But yeah, so a lot of the medications though, so pre-COVID, so I have my I'm recording this. I have my family up in Canada. I have some cousins that would come down and visit, and I'm not going to say it because I'm recording. Mm-hmm. All right, so now we're going to talk a little bit more about how do we bond all of this stuff together. We've got our molecules, we've got our elements, we got our substances. We need to stick them together. So we have 3 different types of chemical bonds. I already talked about a lot of these. Covalent, sharing is caring, caring is covalent. We have ionic, somebody donates an electron, somebody picks up an electron. We have changed the charges, opposites attract. We have, it's actually called an electrostatic bond. No different than, okay, so you put your clothes in the dryer. Here's an electrostatic bond that's just like an ionic bond. You put your clothes in the dryer, you forget to put in the dryer sheet. You pull your clothes out, what has happened? Your underwear and your socks are all stuck to your pants. And when you pull them off, what happens? Do you hear the crackle?
Yeah,
When
you
you pull
do.
them off? Sometimes you might even see a spark. That's because you're releasing energy by breaking that bond. But what that is electrostatic. It is electricity.
Static electricity.
Static electricity. No different than if I rub the balloon on my head, stick it to the wall. Boop. I've changed the charge of the balloon and opposites attract. That is the equivalent of an ionic bond. The only difference is with our ionic bonds is that we have the exchange of electrons that's changing the charge rather than a physical manipulation. Wow, we have got like the biggest discussion over crap you guys have had removed from your bodies.
We're a game of operation.
I'm saying, my goodness gracious. Hydrogen bond is kind of a hybrid where we do have a covalent bond, but then we have areas in that covalent bond where the charges are different and we get that electrostatic. I have got some pictures that I'm going to show you. H2O is a great example of a hydrogen bond. So I'll get some pictures. We'll get there. So
Can you go
sharing
back
is
real quick,
caring.
please?
Do what? I'm sorry?
I only have the bottom part left.
Yeah, no problem. No problem. Yeah, you guys have had a lot of stuff removed from your body. That's crazy. I've never had anything removed from my body. I have all of my original parts. Let's knock on some wood there though, because if something bizarre is going to happen, it's going to happen to me. Oh my goodness gracious, look at all of this. You guys, we are all, you know what, you guys, we're going to be soulmates because it sounds to me like bizarre health stuff is happening to you too. I thought it was just me. If something weird is going to happen, it's going to happen to me. We'll talk about that later. Yeah, I got West Nile virus and it nearly shut down my kidneys. So that was fun. All right, covalent bonds. Sharing is caring, caring is covalent. Okay, we just keep saying it over and over, strengthening that mental pathway. Now, the thing is with these covalent bonds sharing an electron, we can share more than one. We can have a single where they're only sharing one. We could share a 2, which would be a double covalent bond. We can even share 3, triple covalent bond. And the way that we share these, because remember, we're sharing electrons and the electrons are in a cloud. And so some of these sharing areas are, you can have them shared equally, meaning that both are benefiting the same amount. Or you can have one little atom just kind of very loosely sharing, and that would be sharing unequally. Non-polar means they have the same charge. They're close enough and they're sharing close enough that their charges are the same. If this little guy starts floating out into space and is just loosely tethered, suddenly now it kind of depends on where is the cloud. The cloud is probably going to be closer to this guy, and this guy's just like, So that means that this guy's going to be more negative because he's got more of the cloud. This guy is going to be a little bit more positive, not a difference in the charge enough to attract them, just a slight difference in the charge that we say that they are polar. Polar, we've used that term, polar opposite, meaning the extremes of two edges. Polar simply means a difference. There's a difference in the charge. I'll let you guys, give you guys a second to finish writing that down. While you guys are finished writing that down, I'm gonna go grab a Diet Coke because I can. No, you're not going back up there. Forget it. Go lay down. Go. Go.
I'm sorry, can you explain polar versus non-polar one more time? That
Absolutely. All polar means is a difference. If I said, Hannah, that, oh my God, you and I are, have you heard the term, you and I are polar opposites? Meaning the extremes of the two sides. We are extremely different. That's all the word polar means, different. So if I say that something is polar, it means that they have two different charges. One is a little bit more positive and one is a little bit more negative.
Kind of like bipolar.
Bipolar would be that there is two, and polar just means a difference. So you have your ups and downs, your extremes. Non-polar, non meaning no, polar meaning different, non-polar means not different. They are the same. So when we're referring to these as a charge, non-polar would be no different, meaning that they have the same charge. Polar means different, meaning that we have two different charges. North Pole, South Pole, the two different opposite ends of the planet. Pole. You also have, if you have ever watched a Big Bang Theory, where they went and did an experiment looking for monopoles. Anyway, I'm getting off track now, but that's all it means. When I say the word polar, I just mean different. And if it is not polar, it is not.
how would you be able to share with like two negatives though?
So let me show you here. Okay. Let me get my pen. Actually, I don't need my pen. Oh yeah, let me get my pen. All right, so here I have H2O. And I've got two hydrogen bonds and I have an oxygen. We know that hydrogen has one, and we're going to share with the oxygen. And actually, this planetary model is incorrect. Let me correct this. There, now it's satisfied. All right, do you see how we have more electrons here than here? So we have more electrons on this versus this. So we have one molecule, right? H2O molecule. But do you see how because we have less electrons, this area is going to be slightly more positive? And you see how there's more electrons, so this is slightly more negative. This is a difference in the charges, therefore, it would be considered polar. Does that
Now,
make
is that
sense?
just at random, like which side they gather on?
There's nothing really at random, but for what we want, kind of yes. I mean, we would have, I will go back, don't freak out, don't freak out. So here I have my hydrogen bonds. Here's H2O, here's an H2O, here's an H2O. And there is organization in the chaos. So here we're showing in the picture that they're all bonded the exact same way. They're all carbon copies. Not necessarily. We could have one that's kind of upside down, like Mickey Mouse. But so in that case, yes, it could be random. Where exactly are these hydrogens attaching? Although, again, organized chaos, generally, the hydrogens are going to kind of stick together. And that's the whole premise behind this hydrogen bond, because we have, excuse me. So here we have where all of the electrons are bonded. We're sharing, sharing, sharing. So that's what gives this a little bit more negative. There are no electrons right here. And that's what gives it a little more positive. And that's where we start seeing opposites attract. We've got a positive charge here, negative charge, opposites attract. Positive, negative, opposites attract. So although yes, it does seem kind of chaotic, where are these molecules gonna bond? There really is a purpose behind it. Now we could go in and do a whole, no, I'm not going to because I can't, I'm not functionally able to do a whole organic chemistry class. For what we need, think organized chaos. So does that make a little bit more sense, Hannah? Okay. Ionic bonds, again, I've said it 100 times. I'll say it once more. Ionic bonds is where we gain or lose an electron, changes the charge, electrostatic.
Back to the polar water molecule? I didn't finish that one.
Sure. Here, I'll erase the. There you go. So an ionic bond is where we gain or lose an electron. If I gain an electron, I've taken on something negative, I turn negative. If I've lost an electron, I have lost something negative, and now I'm feeling much more positive. I've gotten rid, I think of electrons kind of like feelings. If I lose negative feelings, I become light, I become positive. If I start taking on negative feelings, suddenly I'm negative and I don't feel good. These two opposites are going to attract. And that is the definition of an ionic bond. Because remember, ion is when we gain or lose an electron. Ionic means ic, the suffix. I don't know how far you guys have gotten in your medical terminology. Have you gotten into your suffixes yet? So you guys now know the suffix ic means pertaining to. Ionic means a bond pertaining to ions. And we now know an ion gains or loses an electron. And so what we're dealing with here is because positive and negative attracts, we have an electrostatic attraction. No different than the underwear on your pants or the balloon on the wall. So that's an ionic bond. Oh, Melissa, you're fine. Oh, ferrets are awful. Ugh. I'm not a fan. I'm sure yours is lovely, but I'm not a fan. My significant other had 2 ferrets when we first met. And oh, now Ace is very angry at me. Now, let me explain. Let me explain. He had 2 ferrets when we first met, and they were awful. And so I would be sitting on the floor. I was playing a video game or something, and I'd be sitting on the floor, and the one would come over, and he would be the sneakiest little sneaky sneak. And he would sneak right up, and he would bite the living tarnation out of me and then run away laughing. And it got to a point where I had so much anxiety that I couldn't even come into his house. I'd be like, oh my God, where is it? Where is it? Oh, where? And it was awful. So he did end up they ended up, he rehomed them, not because of me. I didn't force him to rehome them. Don't think I'm a horrible, awful person. But yeah, these two, the female one was pretty chill, but the male, and they ate everything, his remotes, my shoes, everything. So
Mine's constantly takes my stuff, and it's hard with her. Like everything goes missing.
yeah, and they just destroy stuff, and they're super sneaky sneaks, and nope, not a fan.
It's
But
kinda
that's
like
all you.
Dora the Explorer, where it's like swipe or no swiping. He always takes everything.
You know what? I don't have to like them, but you can. And that's the beauty of having differences that make us interesting to each other. A floof noodle. I like that. Ace, I like that. Floof noodle. All right, here's a picture for you little visual learners. Our go-to for ionic bonds. Now, are there other ionic bonds? Of course there are. This is the one I go to because it's so easy to see. You have your sodium, which is Na, and sodium has one sad, lonely little electron. We're going to do the path of least resistance. We talked about this yesterday. It's much easier for me and takes less energy to get rid of one than it would to find 7 others to satisfy my shell. Chlorine, that is actually converted into chloride, only needs one to satisfy the shell. And so what happens is sodium's like, hey, I have an extra electron. And chlorine is like, I would totally take that off your hands if you're just going to get rid of it. And sodium's like, sure thing, here you go. Bloop. Well, sodium has now lost an electron, which means we've become happy. We've gotten rid of something negative. Chloride has gained an electron, which means we've become a little more negative. We've taken on negative feelings. Opposites attract. Bob's your uncle. We have sodium chloride, which is what?
Table salt.
Yeah, it's just table salt. That's what sodium
Table
chloride.
salt.
Just table salt. Now, the crazy thing about chlorine or chloride, because he only needs one to be satisfied, it makes him super, super, super easy to bond with pretty much a whole bunch of other people. He can bond with things like zinc. You have zinc chloride. You have potassium chloride. You have hydrogen chloride. He's not fussy. If you've got an electron, he's gonna borrow it or take it. He's kind of an electron junkie. He'll just take it from anyone. Here's just another picture showing that electron transfer. So we have ions, right, that have gained or lost an electron. We have ions that become positive, lost an electron. We have ions that have become negative. They have gained an electron. And we just have terms for these. A cation is positive. And the way I remember this is cats make me happy. Cats make me positive. An ion is negative. And you've probably heard these terms before, although it's funny. So when I first started teaching, as you guys know, I am Canadian. So some of the words I say are slightly different, even though I've lived in America longer than I lived in Canada for my life. You know, some of the things you say are ingrained in your brain. And when I was in school, we learned these words as cations and anions. And so when I started teaching all those years ago, I was teaching about cations and anions, and nobody knew what the heck I was talking about. So I learned very quickly that you guys say cation and anion. So yes, Leanna, cations will have lost an electron. We get rid of negative feelings, becoming positive. Anion hangs on and collects negative feelings, and becomes negative. Oh, that is a good one, Sean. Very nice. There's a T in cation, and the T is a positive sign. That's a wonderful way. I love that.
So in sodium chloride, the anion would be chloride, and then sodium would be the cation.
Uh-huh. She got it. Heck yeah. Oh, Sean, you should have taken total credit for that. You should have been like, yeah, I just made that up off the top of my head. You are welcome. Ha ha ha. Always take credit. Hydrogen bonds. Hydrogen bonds are a very weak static bond. And I kind of just showed you a picture of them where you have your hydrogen and oxygen, but the way that they're bonded together, organized chaos, is we have one area that is a little more positive and one area that is a little bit more negative. And when I start taking more and more of these molecules and putting them together, now I have a very weak opposites attract. And it is this weak opposites attract bond that gives water its slippery property, meaning that it is one of the few things, not the only thing, but one of the few things that can be in any of the three states of matter. We know that water can be liquid. You can boil it, turn it into gas, freeze it, turn it into ice, which is a solid, and it very quickly can revert back and forth between these three states. And that's because of this very weak static bond that we're looking at called the hydrogen bond. We also have, oh, I just saw the three letters, DNA. Oh, DNA is so fascinating. You guys don't even know. DNA, you know, it's this, I can't do it with my arms, but it's this double helix. And essentially you have, if you unwound it, you have what looks like a ladder, right? You have something, where's my pen? I need my pen. Pen. If you unwound DNA, oh, come on, pen. There we go. If you unwound it and didn't have a double helix, you would have something that looks like this. And so you have these two sides, and one side has, these are just little proteins, just little amino acids. And this side has little amino acids. And these amino acids will bond specifically with other amino acids, and therefore we have this very weak static bond that holds it together. Why do we want a weak bond holding our DNA together? That doesn't seem good. Don't we want our DNA to just be super, super strong? No, no, the opposite is true, because your DNA is the recipe book, the instruction manual, the blueprint for literally everything that's happening in your body. So when your body, because remember I have like my brain that's controlling it and my body is over here. My body is like, oh no, we are getting super low on this one particular protein. How do we make it? Well, if you're trying to cook something, what do you need? You need a recipe. And the recipe tells you what ingredients and how to mix them together. And so what happens is this DNA, let's say this part specifically of the DNA, is the recipe for the protein I need. So he's just going to unzip it and deliver it out. And then we have the recipe and we can make the protein. And so we need the DNA to be able to easily be broken apart. And that's why it's created with a hydrogen bond. Oh, I love DNA. I could talk about DNA all day long. Here's where I've scribbled all over this. We just talked about this. This is, again, our hydrogen bond.
Can you go back, please? I'm sorry.
Sure thing. No worries. You don't have to ever apologize for asking me to go back. ever, ever. So on the next slide, I did already draw all over it. Okay, is everybody okay so far with our different types of bonds and what is happening?
Yes, ma'am.
Everybody's on the bus? Oh, I love it. It makes me so happy. All right, just let me know when you're good, Alana.
I'm gonna just take a picture of it and then I'll go back and finish.
Well,
it.
and the other thing is, if you go on my Moodle, this PowerPoint is on there. You have access to it anytime you want. I just give it to you. This is basically, my PowerPoints are more for me than you, quite honestly, because I just need something to keep me kind of on track. I know I get off track sometimes, but semi on track. I just give it, this is kind of like me giving you the instructor's notes. All right, so here, ouch. Here I have an example of our hydrogen bond. We just went over this, the organized chaos theory. And we have some reactions. Okay, I'm about to see a bunch of you curl up in the fetal position, because if you've ever taken any kind of chemistry or organic chemistry, yeah, Lizette, you are having a panic attack. Let me tell you, so when I was in college, for my associate's degree, we were required to take a chemistry class. And the college I went to, it went through all the vet tech students were going through this chemistry class, and it was like Chem 1. It should have been like the definition of an equation. No, the guy that was teaching the class was a PhD. I'm actually going to stop share.